She's not only an excellent researcher, but she is also a wonderful person, and she gives very nice lectures. So we will see now a glimpse of her research in her talk. So the title of her talk is really deep into her topics. So the strange world of fractionalized quantum numbers in quantum matter. So please, Nandini, the floor is yours.
Well, thank you so much, Rosaire, for such a kind introduction, and to to Laura and the organizing committee for allowing me to join you in this wonderful adventure of wow. So the topic I chose kind of fits in with wow, because it is truly spectacular that you can have fundamental particles like the electron, which has a charge E, and it can somehow get fractionalized in quantum matter. And that is truly a wow event. Or you can have a spin of an electron, again, a fundamental angular momentum, and it can somehow get fractionalized. And that's the story I want to tell. And given that we have researchers in many different branches of physics, I want to also give you the big footprint of this area. So it's an area that brings quantum matter and quantum information together. Yeah. And you can certainly bring them together very easily in PowerPoint, but even truly in the fields converging, this is a new growth area in physics. So let me start with how for millennia we have looked up at the universe and found such fascination among the stars and galaxies. And I'm going to turn my view in the opposite direction and convert that telescope into a microscope and look inside a black pellet. And you might say, well, what could be so exciting about a black pellet? And this is best captured by William Blake in his poem, "To see a world in a grain of sand and heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour." And that's the journey I want to take you on, the black pellet and what lies inside it. Okay, so the story is you have to understand quantum mechanics at many levels deeply. And I'm going to start very quickly by telling you about one particle wave and the quantum mechanics at a one particle level, single electron level, two particle level, and then building up all the way to a quantum material with n particles in it. So the Nobel Prize in 2022 celebrates these three researchers for their discovery of entanglement, for their demonstration of entanglement between photons. And that'll be a big topic today. What precisely is entanglement and why are we interested in it? And right away, we could see people saw that it was recognized for even applications beyond the fundamental discovery in quantum technology. The real hero of this topic, though, is John Bell, who in 1960s took something that was a philosophical debate and brought it into the scientific forum by making a very precise prediction of what would need to be measured to establish that we have quantum entanglement. Unfortunately, he passed away before the Nobel Prize. Okay, so what is quantum entanglement? Why are we interested in this? Why was it worthy of a Nobel Prize? And what are the next steps? And it's the last question that I will dwell on. Okay, so on a very rapid journey, let's start with this two-slit experiment. So I have a source which is sending out one electron at a time. It passes through two slits, and then we observe on this detector. And we all know if we do this experiment with peas, you can shoot peas from a small device, and it will make basically the picture of the slits on the other side. On the other hand, if you have water waves and it passes through two holes, then you get these radiating waves from each hole. They interfere and you get this beautiful black and white pattern on the detector. So the main physics is particles create P-like patterns, waves create interference patterns. And now there was this beautiful, absolutely stunning experiment in 1986 by Tonomura, where they took single electrons, passed them through two slits and observed on the detector. And what you see is, you see these dots every time an electron is detected. So that tells you this electron behaves like a P. You can detect the whole electron. But then if you keep this going for a while, and let me just speed it up here. If you keep this going for a while, you can see at the end, rather remarkably, from all those little dots, a dark and light pattern has emerged, indicating that the electron was behaving both as a particle and as a wave. So this itself was a major discovery in quantum mechanics many decades ago. Now, jumping ahead, let me bring in quantum information in the following way. You can think about this electron. It has, in addition to the charge, it has some magnetic moment, or it rotates, and it can have a rotation which can be pointing up or pointing down. And that's one would call a bit. That's how all our information is stored, in these bits with magnetic moments that point up or down. But a quantum bit has more degrees of freedom, like an electron, in which its magnetic moment can point anywhere on a sphere. And it's this single wave function that we saw in this experiment I just showed you. Now, let us bring two of these electrons together and ask, are there some additional correlations that happen because of the two electrons? So that is now, what we learn now is that when you have two electrons, they could form a two electron state, which we could just separate into what one electron is doing and what the other one is doing. And this would be called a product state. It's not entangled. However, if we make a singlet state of this kind, where electron 1 is up, 2 is down, minus a linear superposition of the opposite configuration, either with a minus sign or a plus sign, that becomes an entangled state, because you cannot separate what 1 and 2 are doing. And notably, it's called the Bell pair, after John Bell. So you might ask, well, that's an entangled state for sure. How far apart can this entanglement live? So certainly we know it lives on the scale of atoms. So two electrons are entangled, for example, in helium. How about if we take these electrons further apart? And that is the experiment Aspey and collaborators did. It was a tabletop experiment where the photons were pushed apart by, say, 10 meters. And even then, there was some connection between the two photon polarizations, even when they were separated by 10 meters. How about even larger distances? That was done by this experiment from the Chinese group. And they looked at 2 points on Earth separated by 1,200 kilometers, and yet there were quantum correlations that remained between the 2 points, even at 1,200 kilometers. So what exactly are these correlations? The entanglement essentially appears in the following way. Two particles, photons, spins, electrons, no matter how distant they are from each other in space and time, they can be inextricably linked in a way that defies the rules of classical behavior. And any measurement on one particle, let's say I told you it was an up-down minus down-up state. So you don't exactly know what electron 1 is doing. It's in a linear superposition of these two possibilities. But if electron 1 is measured, then with 100% probability, you know what electron 2 is doing. If 1 is up, 2 is down. If 1 is down, 2 is up. Until the measurement, it is completely a linear superposition, but the measurement determines what 1 is doing and therefore also what 2 is doing, no matter how far apart. So this is what Einstein called the spooky action at a distance. And these correlations can only happen in a quantum system. So we are noticing some new types of correlations in multi-particle systems that appear only in a quantum system. And this aspect of entanglement is now driving quantum communication and quantum networks through something called teleportation, where you can transmit classical information from you can transmit information over classical networks using a qubit as a resource. So I won't go into this in more detail. I want to ask the next level of question. What can we learn from n particle entanglement? And how do you get n particles? Basically, you turn toward quantum matter. And in quantum matter, you have billions of electrons. And if they can get into a new state of matter that I call, that has been called the quantum spin liquid, this becomes a state of matter with a large degree of quantum entanglement. And it opens up new kinds of applications that cannot be done with just two particles. So that's the broad theme of research in quantum materials, in one aspect of quantum materials. You know, quantum materials is a very broad area, and I've chosen to just tell you the story along this particular axis, just so you can see the wow aspect of this axis. Okay, so let's turn to a quantum material. Typically, these are lattices that have electrons or qubits on every site. So here's a honeycomb lattice with a qubit on every site. And if these qubits interact, so it interacts via these spin operators, sigma I dot sigma j, and on every bond, you have this two-body interaction between the nearest neighbors. And you take these spins, and at high temperatures, they are fluctuating. It's a random, it's a paramagnet. As you cool it, the system typically will order. It will break this rotational symmetry of the spins and spontaneously pick a direction. And depending on the kind of interactions you have, it will order into a ferromagnet or some other pattern. So that has been a very big thrust in the field, to understand these spontaneously broken these spontaneously broken states and how they lead to long-range magnetic order. And that's the way we get our magnets and superconductors and all of these extremely interesting states that the field has been focused on for many years. But now let's change the Hamiltonian a little bit. It looks like a small change, but the results are very different. So what you do here is generate another Hamiltonian with qubits that have particular bond-dependent interactions. So the qubits were isotropic, but on each bond, a different component of the Pauli matrices interact. So say on the blue bond, it's the sigma x interaction, sigma y. On the green bond, and on the red bond, it's sigma z. And you might think, okay, it's still a two-body interaction. What could happen? Now, remarkably, Kitaev was able to solve this problem exactly. And that was very important, because otherwise, if you have approximate ways of solving something, you are never sure whether your result is affected by the approximations. So having an exact solution was a very big deal, and especially in a two-dimensional system. We know many ways of solving problems exactly in 1D, but this was a two-dimensional honeycomb lattice. And what he showed was that if you have these bond-dependent interactions, the spins are unable to order in this long-range magnetic order. But at the same time, it's not like that randomly fluctuating spins at high temperature. It does have a new kind of order that is called topological order. And moreover, this topological order shows up in very complex long-range entanglement patterns of these qubits. And this system is called a quantum spin liquid. So I want to go down this route a little bit and connect it with some of the research in my own group, and also tell you what might be the use of such systems. Okay, so before, let us even see what made this problem so different from when the qubits had completely isotropic interactions. So if you look at, say, a qubit here, you can easily see it is getting three very different instructions from the three neighbors. The blue neighbor says, align along X. The green neighbor says, align along another direction. And the third one says, align along X or Y or Z. So it's like, a totally frustrated situation. You are getting three different instructions from your family, from your friends, from your teachers, and you are like, okay, I'm giving up. I have no idea what I should be doing. And that's exactly what happens here. The spin cannot decide what it should do. And now comes the resolution of that frustration, which is remarkable. The spin decides, and it's not like, it's deciding. That's what the interactions are forcing it to do. The spin gets fractionalized. It's no longer the original qubit. It fractionalizes into new degrees of freedom that are called Majorana fermions. And after fractionalizing, there's an emergence. These fractionalized objects, so for example, one set of fractionalized objects go along these plaquettes, and you can imagine if you have like a flowing, a fractionalized fermion flowing along a plaquette, it becomes like the flux through the plaquette, through the hexagonal plaquette. And another part of the fractionalized spin becomes itinerant. It starts moving around. So to begin with, the qubits were completely localized on the vertices of this hexagon. But after fractionalizing, we have created new degrees of freedom, the fluxes and these itinerant fermions. So that's a very interesting picture of how a strongly correlated system re-emerges with new degrees of freedom. Okay, now what is sitting in these new degrees of freedom? There are these long-range patterns of entanglement. So I showed you two qubits and it formed this singlet state. I'm going to denote it by this little circle. So let's say I have 6 qubits. You can now form many patterns of entanglement. They can form these singlets. This is one pattern. This is a second pattern. Here's a third pattern. And the actual wave function becomes a linear combination. So not only is each qubit a linear combination, but the wave function of many qubits is now a linear superposition of these patterns. And that's the complexity that is now revealed in these wave functions of entangled qubits. So all this sounds really good. We have a model, we have some very interesting entanglement patterns, but can we get real? Can these entanglement states actually appear in materials? And this is where a lot of Rosaire's research also comes in on her work in quantum materials. And can we actually see this signature of topology and fractionalization in materials? So I'm going to give you an answer in the affirmative for both of these. But before I dive in, I want to tell you just how big a deal it is. So quantum matter for the longest time was classified according to the Landau paradigm, the great Landau. And he basically laid out the ways in which you can break certain symmetries spontaneously, and there would be like a local order parameter, like a local magnetization, and that would describe long-range order. Say in magnets or superconductors, all of these fascinating phases of matter. And these states of matter, when you looked at their excitations, like if you flip a spin in a magnet, it would generate spin waves, which would be bosonic excitations. On the other hand, now we are seeing the resurgence, the emergence of another paradigm, a topological paradigm, in which there are again two branches. I call it like integer quantum Hall effect branch, which essentially deals with topological or something that is not a local order parameter, but something topological or more global. And that you can see in bands, like the bands of electrons, the bands of these magnetic excitations, and so on. I am taking you on one of the most exciting journeys of the topological order in the fractional quantum Hall effect branch, where the phenomena that you see are long-range entanglement and fractionalized excitations. So what would be the evidence for this fractionalized excitations? So we need to have a very precise prediction. So here's a model. We need a material, and then we need to have some probes of these emergent states. And I'll just show you one material. It's not a very complicated material. It's just ruthenium trichloride, but it has this very particular kinds of interactions. So this is a lead material. So again, why we call it a quantum material? It's not something you can go and just dig out of the ground. It's not the Stone Age or the Iron Age or something like that. You have to actually have a design principle in mind and then synthesize that. So this is a layered material, weakly coupled layers. And when you look at a particular layer, you see that the ruthenium atoms, which are these purple atoms here in the center, they sit in a cage of chlorine. And I can't go into a lot of chemistry here, but these kinds of octahedral cages are important in lifting some of the degeneracies of the orbitals. So now, so that is what is happening around one ruthenium. If you now look at two rutheniums, here are the two rutheniums around their octahedral cages. They can either interact directly or they can interact via an edge. And now you see there are two pathways by which the ruthenium atoms can interact. And that brings us back literally to the two-slit experiment and that interference pattern. So this is like a little sketch. It shows that you can have an orbital on one ruthenium and it can interact with a different orbital on another ruthenium through one pathway or another pathway. And the interference between these two pathways brings about the very particular bond-dependent interactions. So isn't that beautiful how quantum chemistry and a complex material comes all together to give this very nice Hamiltonian, which has this particular, has this particular kind of order, topological order. So research in my group now decided to take this further and ask whether we can make some sharp predictions for fractionalization. So I'll just show you one result. And this result has to do with comparing the two kinds of magnets. So on the right side, I have the magnet with a bond with interactions that were completely isotropic, sigma dot sigma. And this led to a ground state that has long-range order. When you look at its excitations, you see they are sharp and so this is frequency on the horizontal axis. It tells you I have a magnetic mode, which can be excited. And as you change the magnetic field, so the reason we add a magnetic field is first of all, it's a very good probe of the system. Also, the problem now becomes not exactly solvable, as Kitaev had done. And so we use numerical methods to solve this, called density matrix renormalization group methods and exact diagonalization. And that allows us to see how these modes disperse in a magnetic field. If we now go back to the model which had these bond-dependent interactions, we don't see one mode anymore. We see the modes have split, and that is a signature of fractionalization. We see one mode here, splitting off, a second, a third, and then stuff. And I won't go into more details here, but each of these modes has a very distinct shape in momentum space. And so that is where we can make very particular predictions to go and look for these using neutron scattering and light scattering. Okay, so let me come toward the very end. I've told you about a model. I've told you there are materials and there are ways to probe these. And
so now we are in the 5 minutes, Nandini. That's okay?
Okay. Okay, good. So in the very last part, let me just bring up some more mathematical aspects of these states. How do we really test that there is some kind of topology in these states? And the idea here is you take a wave function at 0 temperature of this highly entangled state that I showed you a picture of. And that's, let's say, the entire system, and you cut it into 2 pieces, A and B. It's very picturesque. What you're trying to ask is A and B, are they product states or are they entangled? And so you break them up and you can construct the entanglement entropy. What is the degree of entanglement between them? And clearly it should scale as the boundary, but if there is this topological order, there is a reduction in that entanglement by an amount gamma, and all the information about the different kinds of fractionalized excitations is sitting in that gamma. So we also have a very concrete way of getting to this entanglement and the kinds of fractionalized excitations through this quantity. So I'll just end with this one result from our group, where we have looked at that Kitaev model in a field, and also we can change the anisotropy of the bonds. And it's a very rich phase diagram. You would think it's such a simple model. How much could be going on in one little model? But it's amazing that in addition to the Kitaev spin liquid, which was known, we have found 2 more quantum spin liquids, which are completely different in character, and they have their own independent signatures in experiments. Okay, so let me conclude then by answering the questions I raised. Can we get entangled states in materials? And the answer is yes, by designing materials very conscientiously and looking for states that are called quantum spin liquids. And why are such entangled states interesting? They are basically producing a new paradigm for defining phases of matter and showing us the role of topology and symmetry. Topology was not something that we studied much in quantum materials, but it has become quite center stage in this paradigm beyond the Landau paradigm. And now you can go forward and ask, why are such entangled states useful? And the key reason people are interested in this is the excitations, because of the entanglement, are highly correlated. So you can use them to make topological qubits. You remember on the honeycomb, I had put a qubit at every site. If you made a real material, that qubit would be interacting with the environment and it would decohere. On the other hand, if you take the excitations, emergent excitations, and make qubits out of those, they are highly entangled. So even if one qubit dithers, the other qubit is controlling it through the entanglement patterns. And that's why this becomes such an amazing platform for creating topological qubits for quantum computers. Okay, at the very end, I'll just take 1 minute to say that this fractionalization is a big phenomenon, not just in this one model or one material. You can have a single electron charge fractionalizing in fractional quantum Hall effect. You can have, so these are all the wow moments. You can have electron with spin and charge that we always know come together to separate in a Luttinger liquid. You can have magnons which have spin 1 bosonic excitations fractionalize into spin-half neutral spin-ons, and these spin-ons can make Fermi surfaces. And you can get monopoles, which never exist in vacuum, but you can get monopoles in pyrochlore spin ices. So with that, let me end. Let me thank my group. They have been instrumental in getting our research to this point. It was very recent research, started in 2018, and all of my group has been instrumental in making progress toward this unified goal. And I want to leave you with this picture of when you're in difficulty, almost a life lesson, strongly interacting systems, you're facing frustration, don't give up, fractionalize. It's not a bad thing if you break apart and fractionalize, because something new will emerge. So thank you.
Thank you very much, Nandini, for this wonderful talk. And in fact, this last slide is really very up to the point of what you were presenting. So now the floor is open for questions or discussions. So please put your questions in the chat and we will read them for you. And I see that I have the first question. So let me just read it. This is from Olga Soloveva, and she's asking whether quantum spin liquid can be applied today. Can you think of some application in industry, for instance?
Yeah, that's a good question. This is going back to where we are trying to. So at this point, this is where we are in our research on this topic. Let me go back to that material. So, at this point, we have candidate materials, and there are several experiments that are being done to establish that they have these fractionalized excitations. So the steps toward making something more useful is, once we have these fractionalized excitations, you need to demonstrate braiding. So you need to be able to take one excitation around another excitation and then use that as a topological qubit. So we are still some time away from that. And I would say at the rapidity with which things are moving, I would say in another 5 years, we should be in a position where we have detected them and we are at the next stage of actually applying them for some application.
Thank you very much. We have now a question by Nafi Farsana. She's asking, is pilot waves hypothesis not, wait a second, do pilot waves a hypothesis not account for entanglement?
If you're thinking about like the hidden variable theory, so initially there was, so this aspect of spooky action at a distance, you basically observe one of the qubits and the other one essentially gets determined, or you can say collapses into its opposite state. This was initially, people had a lot of difficulty with this, including Einstein. That's why he called it, this is spooky action at a distance. And there were these hidden theories, hidden variable theories, that along with what you're observing, there are some other degrees that you cannot observe. And that is where John Bell played a very central role by proposing a particular inequality in terms of correlators that you measure in different polarizers, different orientation of the polarizers. And that was able to, the observation of Aspey and collaborators was able to show that the hidden variable theory will not account for these quantum correlations that are present in entanglement. So now we know definitively that the correlations in entanglement are not going to be able to be reproduced by any, no matter how complicated a classical theory you make.
Thank you very much. There is a question by Lisa, and she's asking, could you explain the measurements made to obtain the graphs with the different modes a bit more? What do the J and K parameters mean in your explanation of the models?
Okay, let me quickly go to this one. Okay, so what J basically means, I have, let's say, two qubits or two spins. Let's think of them as spins. Here are the two spins oppositely aligned on the nearby qubits. Let's say if they were aligned in the same way, then this one qubit couldn't hop there because there is a Pauli exclusion. But if they are aligned oppositely, this up qubit can hop there and hop back, and hop there, and the down one can hop there. So there can be an exchange. So this J is a measure of this exchange interaction between qubits. Okay. And K similarly is also an exchange interaction. So K is also some exchange interaction between qubits, but it generates an anisotropic interaction because of that interference pattern of the exchange pathways between the two qubits.
Thank you very much.
So bottom line, just to answer your question, where is it coming from? It's coming from the overlap of orbitals. Ultimately, we have to go into the quantum chemistry, and it's the overlap of orbitals and the Coulomb interactions. So you cannot get magnetism if you don't have Coulomb interactions. So ultimately, it's coming from the overlap of orbitals and the Coulomb interactions when two electrons come to the same site.
Maybe the last question by Radhika. The question is whether you could suggest some books that can be freely accessed, where they give details about what you have been talking about. That's the question.
I would say all of you guys are very savvy about just Googling, and you could at some level just type in quantum spin liquids and number of resources will come up. Or here is a very nice, it's a real tome, but you could also just explore this article. But there are review articles, and I should really have put some references here. That was one of the problems. I was not able to. There's a huge body of work, but there are review articles on quantum spin liquids. You could look for Broholm, Broholm et al. It's a review article with experimentalists and theorists together, and that would probably be more accessible.
Thank you very much, Nandini. Thank you very much again for the talk, for the